Welcome to the 12th lecture in abstract algebra. The topics that we'll explore in this lecture include commutativity versus anti-commutativity, an introduction to finite groups, and the quaternion group.
Okay, so we'll start with the definition of anti-commutativity. Let the set G, together with some binary operation star, be a magma. The operation star is anti-commutative over the set G if and only if, for every pair of elements A and B in the set G, we have that A star B is equal to B star A only when A and B are the same element. That is, if A is not equal to B, then A star B is never equal to B star A. Now, if the operation star is anti-commutative, over the set G, then the elements of the set G are said to anti-commute under the operation star. So if an operation is anti-commutative, then it is not commutative. These properties, these two properties, are mutually exclusive. However, if an operation is not commutative, this does not imply that it is anti-commutative. So there is no dichotomy. An operation does not have to be one or the other. In fact, it can be neither commutative nor anti-commutative. So in particular, if a set G together with some binary operation star is a group, then the operation star cannot be anti-commutative over the entire underlying set, since the identity element commutes with every element in the set G and an element and its inverse must commute. Now, if a set G is a group under addition, we can give an alternate definition of anti-commutativity. So let the set G under addition be a group, and let the same underlying set G together with the binary operation star be a magma. The operation star is anti-commutative over the entire set G if and only if for each pair of elements A and B in the underlying set G we have that A star B is equal to the negative of B star A. That is, A star B and B star A are additive inverses of one another. Okay, so now we'll begin to look at some examples. So first, we will show that the integers under the operation of subtraction is an anti-commutative quasigroup but is neither a semigroup nor a loop. So proof. Let A and B be two integers. Then the difference, A minus B, is an integer. Further, A minus B is the negative of B minus A. So the operation of subtraction is both closed and anti-commutative over the integers. Now notice that 1 minus the quantity, 2 minus 3, is 1 minus negative 1, which gives 2, and the quantity 1 minus 2 minus 3 is negative 1 minus 3, which gives negative 4. And so the operation of subtraction is not associative. Over the integers, and hence the structure consisting of the integers under subtraction is not a semigroup. Now notice that for every pair of integers A and B. There exist unique integers, x and y, such that a minus x gives b, and y minus a gives b, namely, x is a minus b, and y is b minus the negative of a. I'm writing it this way so that we're using only the operation that's in the structure. And hence the structure consisting of the integers under subtraction is a quasigroup. Now suppose that a minus an element e gives the element a, then e must be 0. Now suppose that e minus a gives the element a, then e must be a minus the negative of a, or we can think of this as 2a, and this is not 0 unless a is 0. And so there does not exist an element in the set of integers such that for every integer a, we have that a minus e is the same as e minus a, which gives a. And hence the integers under subtraction is not a loop. So we have demonstrated that the integers under subtraction is an anti-commutative quasigroup, but is neither a semigroup nor a loop. Okay, next example. The set of complex numbers together with the binary operation star, where star is defined by z sub 1 star z sub 2 is the product of z sub 1 with the conjugate of z sub 2. The structure is a quasigroup, but is neither a semigroup nor a loop. Further, the operation star is neither commutative nor anti-commutative. Over the complex numbers. So proof. We have already demonstrated that the structure is a magma, but is not a semigroup, since the operation star is not associative, over the complex numbers. And since z sub 1 times the conjugate of z sub 2 is not the same as z sub 2 times the conjugate of z sub 1, and the product of z sub 1 with the conjugate of z sub 2 is not the same as the negative of z sub 2 times the conjugate of z sub 1, the operation star is neither commutative nor anti-commutative over the complex numbers. Now notice that for every pair of complex numbers, z1 and z2, there exist unique complex numbers x and y, such that z sub 1 star x gives z sub 2, and y star z sub 1 gives z sub 2, namely, x is the conjugate of the quotient z1 over z2, and y is the product of z2 with the conjugate of the reciprocal of z1. And hence the complex numbers under this binary operation star is a quasigroup. Now suppose that z1 star e, well, let's just use z star e gives z. Then we have that z times the conjugate of e gives z. So the conjugate of e is z over z, which is 1. And so e is 1. So now suppose that e star z gives the element z. Then e times the conjugate of z is z. And so e is z over the conjugate of z. And this is not equal to 1 unless z is a real number. And so there does not exist an element e in the set of complex numbers such that for every complex number z, we have that e star z is the same as z star e, which gives z. And hence the structure is not a loop. So we have demonstrated that this structure is a non-commutative quasigroup, but is neither the semigroup nor a loop. Further, the operation star is not anti-commutative over the set of complex numbers. Okay, new example. The set of complex numbers together with the binary operation star prime where star prime is defined by z1 star prime z2 is the conjugate of the product z1 z2. The structure is a commutative quasigroup but is neither a semigroup nor a loop. So proof, let z sub I be a complex number, then the conjugate of the product z1 z2 is a complex number. Further, the conjugate of the product z1 z2 is the same as the conjugate of the product z2 z1. So the operation star prime is both closed and commutative over, so they're complex numbers. Now z1 star prime the quantity, z2 star prime z3 is z1 star prime the product of the conjugate, or rather the conjugate of the product z2 z3. This is the conjugate of the product of z1 with the conjugate of the product z2 z3, and so this is the conjugate of z1 times z2 times z3. Now the quantity z1 star prime z2 star prime z3 is the conjugate of the product z1 z2 star prime z3, and so this is the conjugate of the product z1 z2 with z3, and so this is z1 times z2 times the conjugate of z3. Now in general, the conjugate of z1 times z2 times z3 is not equal to z1 times z2 times the conjugate of z3. So the operation star prime is not associative over the complex numbers, and hence the structure, complex numbers together with operation star prime, is not a semigroup.